Okay. So calorimetry is the measurement of heat. And what you would do in real life is you would take your chemicals, they're probably a solution, and put them in an insulated container. So my container actually now has thick insulated walls. When you do this for real, you also put a lid on this, and it's called the bomb calorimeter because you don't let any of the pressure that's inside the reaction escape. You keep everything in. But if you just take 2 styrofoam coffee cups and you stack them on top of each other, enough of the heat is trapped inside this, especially even if you put a little plastic lid on it. Enough heat is trapped inside the styrofoam that you can measure the temperature change. The temperature change in these reactions usually happens pretty rapidly. Those of you who have done the endo-exo experiment for this week know that the temperature change happens over the course of just a few seconds. And then that temperature change, that heat gets transferred to the thermometer, and then you read the thermometer. So we'd actually use an electronic device, not a thermometer, but this is good just for the show, right? So I take some A and I take some B, and I put them both into this insulated vessel. And then I measure how much heat is either taken in or given out. And it follows this equation. The Q equals MC delta T. Q is the amount of heat. Now, heat is an energy, so this is the amount of heat energy. What do we measure energy in? I said that, but yeah, just a little bit louder. We're going to measure that in joules. There is actually a competing unit of energy that's very, very good. It's a very useful unit. We're not going to use it, but you've all heard of it, and people in other departments use it. What's another unit of energy other than the joule? What is power? And power is work per time or something. I don't even know what power is anymore. It's the calorie. Calorie is a unit of energy. And the calories definition is really, really simple. It's why people still use it. The calorie is the amount of heat required to raise 1 gram of water by 1 degree Celsius. That's a really good definition for a unit. Nice and simple. Take 1 gram of water, make it get 1 degree hotter. That's 1 calorie. Okay. I've lost my blank pen. I put it down somewhere. I don't know where it is. Did it roll on? Standing up. M is the mass of the whole reaction. It's the combined mass of A and B. Now, A and B are probably solutions. So we probably administered them into this calorimeter as volumes. So we might have to convert volumes into mass. That's a very easy thing to do because everything that we're going to do is dissolved in water. And the density of water is 1 gram per milliliter. So every milliliter I put into the reactor is worth 1 gram. Okay. This is the mass of everything in the reaction. So that's going to be in grams. How do we get to the grams? Well, we know that the density of water is 1 gram per milliliter, and density is mass per volume. If density is mass per volume, what does mass equal? Because I might have to find that value m from a volume, right? To convert my volumes into masses. If D equals m over V, what does m equal? Leave the mass where it is, bring the volume across the equal sign, it goes from being a denominator up to being a numerator. M equals V times D. Okay? All right, C is a special number. I'm going to do that one last. This is delta T. What did we already say delta meant? Delta is the symbol that we use when we're looking at change. If it's a capital delta, that's a change that we're expecting to be, a real number. If it's a lowercase delta, then we're expecting a small number. So this is the temperature change. What should my units be for temperature change? Kelvin will do. Does it have to be Kelvin? Why not? If I did a reaction and it started at 20 degrees and it went up to 24 degrees, and that was degrees Celsius, then the change in temperature is 4 degrees, right? What is 20 degrees Celsius when you express it as Kelvin? 293, because we're going to add 273 to that value. And then it goes up to 24, which would be 297. So the change in temperature is 4 Kelvin. When we're talking about changes, the importance of the units goes away. Okay? Don't use Fahrenheit, because Fahrenheit's not it's not the same. It's not on the same scale. But you can use either degrees Celsius or Kelvin, because it's the same number. And because our thermometers read in degrees Celsius, that's going to be an acceptable number for us. Okay. If you were doing a calculation, and we'll do some of these in a chapter or two from now when we look at gases, and you're just using the value of temperature, that value needs to be in Kelvin. But if I'm looking at the change in temperature, then the importance of the unit goes away. This missing value here is the heat capacity. And heat capacity is a constant, but it belongs to the material that you are looking at. It is specific to the thing that you are looking at. You've all encountered specific heat capacity at some point in your life. You just haven't really recognized it for what it is, but it's always been there. Anybody ever been unfortunate enough to have to eat, they're called TV dinners? You go to the supermarket and you buy food that comes in cardboard boxes. And when you open the cardboard box, inside there's a plastic box. And then you put that plastic box into the microwave and you cook the food. And it could be like Salisbury steak and gravy and mashed potatoes and green beans. And you put it in the microwave for however long it says to do on the box. And when it comes out, the potatoes are so hot you think that they're going to burn a hole through the container. But the brown Salisbury steak is still cold. That's heat capacity. That the potatoes accepted heat a lot more readily than the protein did. It's just heat capacity. How good are you at holding on to heat? That's all this is. And every different material that we can think of is going to have its own heat capacity. And because the world is full of scientists and engineers, and there have been for several hundred years now, all of these numbers are written down somewhere. If you want to know what the heat capacity of fill in the blank is, you can go look that up because somebody has tested it. It's also the basis of like everything you ever needed to know about weather. It's all heat capacity. Anybody been to the desert? What's it like in the daytime? What's the desert like in the daytime? It's hot. What's it like at nighttime? It's cold. Anybody ever been to the beach? What's it like in the daytime? It's hot. And what's it like at nighttime? It's still warm at nighttime at the beach. Because water is slow to warm up and also slow to lose its heat, whereas sand gets hot and then loses its heat straight away. So we get these big temperature differences in landlocked countries. Snows in Minnesota, like all the time, because it's not near a big enough body of water to ever keep that place warm enough. Whereas you go live on an island, people say, oh, we're going to retire and go live on an island. They don't mean a cold one. They mean one that stays warm during the summer because it doesn't get baking hot, and it stays warm in the winter because it doesn't get baking cold. What's the opposite? Cold, freezing cold. Because the water is temperate, it stays in the middle, slow to warm up, slow to cool down, holds on to its heat. The specific heat capacity for water, if we're talking about calories, 1 gram, 1 degree Celsius. This would be set to 1. In joules, this value is 4.184. Okay, so if Q equals mc delta T, this is in joules, and that's in grams, and this is in degrees Celsius. What are the units for heat capacity? If Q equals mc delta T, and I want to know what C is equal to. C is Q divided by M divided by delta T, which is joules per gram per Celsius. Okay? or Kelvin. The degrees Celsius and Kelvin are interchangeable in this instance. Okay. Let's do one. What do we need to know? We need density. Okay. Even if A is an acid and B is a base, they're dissolved in water. And when the acid and the base react with each other, and all acid-base reactions are exothermic, they all give out heat. When they react with each other, the first thing that they do is give that heat to what they're dissolved in. So they give it to the water, and then the water passes it along to the thermometer. That's the heat capacity that we have to think about. And we can find the mass of the volume that's inside the reactor by just multiplying it by its density. And for water, that density is 1. Okay, let's do a question. So we've got a couple of things coming your way. Next week, you have a virtual lab activity where you're going to do an acid-base neutralization. All acid-base neutralizations are exothermic. They all give out heat. You're going to do a practice run of that in the virtual environment first, and then the week after fall break, you'll come into the lab and you'll do a real one in this lab with some styrofoam coffee cups. And we'll measure how much heat gets given out, and you'll do the calculations, and you'll find out what its enthalpy of reaction is. Okay. I wrote some numbers down. If I took 100 milliliters of 2.5 molar HCl, and I took 100 milliliters of 2.5 molar sodium hydroxide. When they react, they increase the temperature from 20 degrees Celsius to 37.1 degrees Celsius. We're going to ask you to do 2 things. You do not know how to do the second part yet. You do, however, know how to do the first part. You know how to find the heat Q. Okay. We're going to have you figure this out. Q equals MC delta T. We'll get another one or 2. Calculate the amount of heat that this reaction generates.
Thank you.
Things you need to take into account. Q equals MC delta T. The density of water is 1 gram per milliliter.
Yeah,
So,
yeah. No,
I know, she's just been texting me, so it's really good.
yeah, I had a quick word with Dan. Dan's having a space in. Yeah. Only a couple of things. But I've got a
Oh, we have to write it.
spaces. Some of her ideas.
He does it. We do this. Yeah. He did that before.
Joshua, do you have a mask? There's a box of masks at the back of the room.
Get yourself a mask. Don't take it off. Okay, sorry. How is doing over Vietnam? Okay. Why not? What are you holding up? What is that? Oh. Yeah. Okay. Okay. Yes. Yes.
Okay, all right, let's think. We need this number and we need that number. Let's think what I've got. I've got a styrofoam coffee cup and I've taken 100 milliliters of acid. That's a little bit of acid dissolved in a lot of water. So this really is 100 milliliters of water that's gone in here. It is aqueous acid, right? And then I take 100 milliliters of base. Well, what's the base dissolved in? The base is dissolved in water. So that AQ tells us this is mostly water. And 100 milliliters at 1 gram per milliliter, that's 100 grams. And this is 100 grams. So how much is in my container?
200 grams.
In the question. Find the value of Q.
Is that it done with the painting now? No more paintings from you?
Sculpture?
I started a new one,
What are you doing? What are you painting?
I don't know how to explain. It's like kind of abstract, like picture,
Yeah, don't make me.
You have M. M is the mass of everything in your reaction. Everything in the reaction that's combined, combined mass. That's the mass of water that you are going to be heating up when this reaction gives out its energy. Ooh, that's right. Yeah, like 14,305.05 or something somebody told me this morning. Okay, well, I'm going to scrub them off anyway. We're not going to use them. How many significant figures am I allowed to keep? I say 3, which is 14,300 joules. Oh, do we have another way of describing 14,000 joules? How many grams in a kilogram? 1,000. The answer is always 1,000, people. The answer is always 1,000. How many grams in a kilogram? 1,000. How many joules in a kilojoule? 14 kilojoules is a sizable amount of energy. That's enough energy to turn 200 milliliters, which is a small volume of liquid, and raise its temperature by 17 degrees. That's quite a lot. That energy is given out. It's an exothermic reaction because the net ionic equation for all acids and bases is acid, H+, plus base, OH minus, makes water, H2O. And water covers 70% of this planet's surface because it's an exceptionally stable molecule. You do not get to be abundant in nature unless you are low in energy. Okay, so when we say something is stable, it's low in energy. So our reactants are higher in energy than our products were. They gave that excess heat away. It's quite a lot. Okay, that's Q. Q never gets mentioned again in the book after you find it this one time. The rest of the book wants to know enthalpy. Enthalpy change. So that was part A. And I said you don't know how to do part B. Here's how you do part B. Part B is, now that you've found heat, find the enthalpy change, the delta H. Well, it turns out that all delta H is Q per mole. That's it. You know those other numbers that are in the question that you might have pondered over and you didn't end up using, but they were still in the question? It's time to use them now. I need to find out how many moles of acid did I neutralize in order to make that 17 degrees of temperature change. So I need an equation that says moles equals something. What does moles equal? Absolutely it does. The first thing that should come to your head is that moles equals mass divided by formula mass. Not in this question, because this question doesn't contain masses. But moles appears somewhere else. The other time that it shows up is that molarity equals what? Molarity is moles per liter. And look what's in the question. There's a molarity and there's a volume. It's not in liters. But I know how many milliliters are in a liter. How many milliliters are in a liter? It's always 1,000. So I'm going to convert that into liters. And I'm going to use this other number to find the value of moles. So if molarity is moles divided by liters, what is moles equal?
0.25.
Oh, you're reading out the question now. I just mean in terms of this. Moles equals molarity times liters. This has to be liters, not just a volume. It must be in liters. Okay? Now, one of the things that becomes apparent to students, chemistry majors, to do a lot of this, is that sometimes the books say kilojoules, and sometimes they say kilojoules per mole, even though they're still talking about enthalpy changes. And nobody ever explains it to them. It's never ever going to be written in the book. And you only get to notice it after you do this multiple times. The question comes because of this. If I say that enthalpy is heat per mole, what do I mean? Moles of what? Do I mean moles of acid that are being neutralized? Do I mean moles of base that are being neutralized? Do I mean moles of water being produced? Do I mean moles of salt being produced? This is kind of awkward. So for reactions, where you have reactants and products, all of those are always just quoted as kilojoules. Even though they are kilojoules per mole, they're just quoted as kilojoules because we don't know exactly what it means. We don't know that the way that we see it is the way that you are going to be looking at it next. I'm talking about the amount of acid that gets neutralized. You're talking about the amount of water that gets made. But the number is still the same number. Okay. What's the number? This is your part B. Get to it. Delta H is Q over moles. Q comes from the previous answer. Was it 0.3 or 0.1?
I was expecting more, but it could be so.
This question was provided to you nicely. Think about this. Acid plus base makes water plus salt, okay? That number, this set of numbers, and that set of numbers are the same set of numbers. So there is no limiting reactant. There is no limiting reagent here. If there was, that would be the number that you would go hunting after. but I made the moles of both of these be identical. So you only have to find one. Technically, I think the best description here is what are the numbers of moles of water being made? I think that's the best description.
I believe you. I don't know whether you do or not.
Moles is molarity times liters. Capital M literally means moles per liter. So my volume is in milliliters, but I need a conversion factor that's going to make those liters go away. So the conversion factor that tells me there's 1,000 milliliters in a liter puts the liter on the top. Just make the liters go away. That 1,000 milliliters are in a liter. And then I have 100 milliliters. And look, the milliliters just cancel too. Oh, I've got to go back and fix part A as well. Can't come onto the board until we've fixed it. You'll see it at the end. So what's your answer? Okay. 57.2 what? Kilojoules per mole. Anybody else agree? Yes. Okay. All right. So if I gave you this as a quiz question and you answered part A and part B, and part A was 14,300 joules and part B was 57.2 kilojoules. If this is a 10-point quiz, have you earned 10 points? You've done a completely worked example. There was a diagram at one point with the little thing and like a coffee cup and solutions going into it. Surely that's enough for all of the points. A worked calculation with the units in the calculation and the dimensional analysis stuff, surely that's worth 10 points. It isn't. I'm giving you a 6 or a 7. Seems a bit harsh. What have they done wrong? My attempt at a balanced equation right there. It's not that. Energies have a magnitude and a direction. These two answers are magnitudes, but they have no direction. Is this energy going into the reaction or coming out of the reaction? Is it coming out, going in? Did it get hotter or did it get colder? It got hotter. So the heat is coming out. Are these positive values or negative values? Are they positive values or negative values? Heat is being lost. That's now a 10-point answer. You told me a magnitude, but you did not tell me a direction. Energy has magnitude and direction. If you only tell me one of them, you've told me half of the answer. Not giving you more than 8 points for that. Maybe 7. Maybe 6. Energies have a magnitude and a direction, which is what we're going to be doing next. If you look on Blackboard, I've got an example of it. There's something called the Hess's Law worksheet. We're going to go through this Friday. It's just lots of examples, and that's all we're going to do Fridays, mathematical example after mathematical example. Here's the principle. It's called Hess's Law. Because energies have a magnitude and a direction, we can add them together. If we pretend that I-35 runs due north, completely north, north-south, how far is it from Austin to Dallas? Hours isn't going to work for me. I'm asking for a distance. How far, what's the distance between Austin and Dallas? That's about 180 miles, but that's only half the answer. It's 180 miles north. How far is it from Austin to Waco? It's 90 miles. 90 miles north. Okay. How far is it from Dallas to Waco? From Dallas to Waco gets to be 90 miles south, because this adds to that to make this. And if we go in this direction, we call it north, and if we go in this direction, we call it south. When heat leaves the container, we call it negative. When heat goes back into the container, we call it positive. If you start the day in Austin and you go to Dallas and then you come back and you park in exactly the same space, I don't care how many miles it says your car has done, you have not moved. You have not moved. You're back where you started with. Hess's law says that if you turn A into B and then B into C and then C into D and then D back into A, the total energy in that loop is 0. Energies are additive, they have a magnitude, they have a direction. If you can understand that, you can understand question 1 on the worksheet. I'm going to do it, but I'm going to show it to you. If you are told that the enthalpy change for that first reaction is 640 kilojoules exothermic, and the bottom one is 886 kilojoules exothermic, then you should be able to find out how much energy is involved in this reaction without even having to do it. Because that is Austin and that is Dallas. And that is Austin and that is Waco. And this is Waco and that's Dallas. We start with the phosphorus and we add 3 chlorines to it. Or we start with the phosphorus and we add 5 chlorines to it. Or we could start in the middle with the phosphorus that already has 3 chlorines to it and find out what is the distance until you get 5. If you can do this, everybody can do this, right? If you can do this, you can do those. And the fact that somebody has already done all of the reactions that you can ever think about, they've already been performed, they've already been cataloged, we can find out whether this is exothermic or endothermic and by how much before we even have to do it. Friday, take a look at this, print it if you want to. I suggest you do. The Hess's Law worksheet. It is somewhere on Blackboard. I think it's probably in chapter 5. We will do nothing on Friday other than worked examples. Okay? See you Friday.